Next, we will discuss storage tiering and differentiated high availability in TiDB. Our previous discussion revolved around resource control. Next, we will look at features we can use to implement high availability in our TiDB clusters. The first one we'll look at is data replication. On the left-hand side of the diagram, it shows traditional single-tenant databases. Remember, there are many definitions of single and multi-tenant. In the TiDB world, a tenant is an application. A single-tenant database is used for a single application, and a multi-tenant database such as TiDB can effectively run many applications. So we're thinking of this in the data consolidation world. So in our diagram, DB1 is a single database that does not implement any data replication. There's one replica, and that's not even really true. There are no replicas. There's one copy of the data. DB2, on the other hand, has a primary database and a single standby database. There are two copies of the data. One is in the primary, and the second is a replica. DB3 has a primary database and two standby instances. There are three copies of the data. So primary copy of the data and two replicas. So adding replicas in this environment is difficult. It means you'd have to create new database instances and do a lot of stuff on the back end to connect them. Now let's look to the right-hand side of the diagram. This is what our three databases would look like if we did a complete database consolidation project to move DB1, DB2, and DB3 to the multi-tenant TiDB cluster. TiDB implements data replication by default. Notice that there are three servers and each one stores replicas of the data. This means if servers go down, we don't lose data. So when we're doing database consolidation, if the multi-tenant database can't customize the number of replicas for data in each tenant, the situation shown in the diagram will occur. That means we must meet the requirements of the tenant with the highest demand for high availability. In our example, that's database 3 or DB3 with its requirement for 3 copies of the data. To achieve this, we must reserve 3 independent multi-tenant database servers to meet the high availability requirements of the DB3 tenant with the highest demand. Keep in mind, DB1 and DB2 do not require such a high level of availability. It's recommended that they have 2 replicas, right? Just like DB3, that is 3 copies of the data. Hey, more is always better, right? Well, this is not what we want. We need a way to deal with this. Notice the change on the right side of the diagram. This matches the original environment. From a cost control and operational workload perspective, allocating a database 2 replicas, which is actually 3 copies of the data, seems somewhat wasteful. Of course, some multi-tenant databases may not need as many replicas for DB1 and DB2 as they have for DB3. The problem with this approach is that the multi-tenant servers prepared solely for DB3's high availability may also end up being idle and wasteful. We need a way to accommodate all levels of availability. In TiDB, compute and storage are separate. The storage layer is TiKV. It stores data as key value pairs. The storage layer is responsible only for storing and accessing data. TiDB server is the compute layer. It handles SQL processing, but it can push some filtering down to the TiKV layer. This helps with performance. You can scale storage and compute separately in a TiDB cluster. So let's take a look at our diagram. Look at Table 1 and Table 3. These 2 tables have typical high availability requirements. Notice that they have 3 replicas. Here's Table 1. Here's Table 3. Let's compare these 2 tables to Table 2. Table 2 is critical to our business and has a more strenuous high availability requirements. In fact, we've determined that we need 5 replicas for Table 2. So the question is, how do we configure this? Well, we will use TiDB placement rules to do this. First, we create a placement policy. Placement policy is another way of saying placement rule. We will name our placement policy P2, and we will use the followers option to set the number of replicas. In this case, we set the number of followers to 4, which gives us 5 copies of the data, or 5 replicas. Next, we issue a create table statement for table 2. We include the placement policy option. Notice that we set this to P2. This means that table 2 will have 5 copies of the data. Now we can customize the high availability level separately for each table and each partition. Compared with being only able to customize the high availability level for different tenants, this fine-grained control can save us a lot of resources. Next up is storage tiering. Storage tiering is accomplished using the concept of hot and cold data. Hot data refers to current data, such as product orders from the last month and user payments records from the last week. That is, data that we need to frequently query. Ideally, this data would be stored on high-performance disks such as SSDs. In contrast, cold data refers to historical data generated during past years of application operation, such as transaction records from the last 10 years, which may be rarely or even never queried again. It would be best to store this data on less expensive HDDs. This helps us save money on our database environment. In the design of a single-tenant database, some applications may have more cold data than hot data. If storing them in one database affects the efficiency of the database, it is necessary to separate them by hot and cold data, such as in database D1 shown in the diagram. By storing the hot and cold data separately in different databases, we save money and make it more efficient, but this type of arrangement would be difficult to manage. There are also some single-tenant databases that use designs such as partition tables, which store hot and cold data in different tables or different partitions within the same table. Periodic processing is performed on the cold data, such as deletion, backup, or migration, such as in the case of DB2 shown in the figure. The database DB3 represents that when designing for a single-tenant user, there was no consideration given to how to separate hot and cold data, or the system has not been running long enough to generate a significant amount of cold data. So the cold data has not yet affected the system's performance. When you migrate single-tenant databases to multi-tenant databases without a solution for separating hot and cold data, there will clearly be a waste of hardware resources. For example, the hot and cold data in DB1 will use the same hardware resources, resulting in an unnecessary cost. When the cold data of DB1 and DB2 are migrated to the multi-tenant database, they occupy high-performance SSD storage. Also, the original partition design of DB2 requires additional attention and manual operation. This increases the DBA and system administrator's cost. After running for a while, DB3 will have too much cold data and will adversely affect its performance. So fortunately, there's a better way. Fortunately, TiDB allows you to deliberately place data into hot and cold areas using placement rules. So TiKV1, 2, and 3 are high-performance storage servers equipped with SSDs. These drives are much more expensive than HDDs. We want to use them to store hot data. In contrast, TiKV4, 5, and 6 are machines with high-capacity HDDs. These disks are slower than SDDs or SSDs, but have very low cost. We want to use them for storing cold data. As before, we will use SQL statements to create our placement rules. So take a look at the create placement statement in the middle of the diagram. This is very similar to the one we saw previously. We will create a placement policy named pcold. We will set 2 parameters, primary_region and regions. This will determine where TiDB stores the data for the tables that pcold placement rule uses. The constraints equal option specifies the disk type, in this case HDD. So when creating tables 3 and 4, we specify their placement policy as pcold. As a result, these tables are placed in an inexpensive storage servers TiKV4, 5, and 6, which, as we mentioned earlier, are designated for storing cold data. The high-performance SSD storage servers, TKV1, 2, and 3, were designated for hot tables, table 1, and table 2 to use. It's important to note that we can partition some historical data, that is cold data, and set it in a separate placement policy. We can also modify the placement policy for a previously hot table or partition so that we can place it on storage servers where cold data lives. We can see that the placement rules in SQL provide fine-grained control for the storage location and high availability of each table in the multi-tenant TiDB environment. This helps us control data objects in the database consolidation process. So far, we've discussed isolation. What we haven't covered is how we want our multi-tenant database to respond to changes in load. Specifically, the changes in the load, really resource demands, of the individual applications. At PingCap, we call this differential scalability requirements. Before we begin, let's define unified storage and compute. It's right there in the title of the slide. It's pretty simple. Unified storage and compute means that compute and storage lives on a single machine. They aren't separated in modern databases like TiDB. In the diagram, tenant D1 has reduced its data volume via data optimization. Its concurrency has not changed, and the load from SQL statements remains the same. The DB2 tenant's data volumes remain unchanged, but there's been an increase in concurrency. This has resulted in a significant rise in queries per second. The DB3 tenant's SQL load and queries per second have not changed, but the data volume has doubled. The load on our three tenants have changed in different ways. Their demand for computing resources has changed too. If you were using a traditional database where compute and storage are coupled, this would pose a problem. You would be forced to implement a sharding strategy where each server provides computing and storage capacity. However, this will lead to difficulties in controlling costs because you can't really fine-tune control changes to each tenant. This also increases the complexity, which will increase DBA costs. An example will help here. Let's assume that in our compute and storage integrated system, DB1, the amount of data has decreased to 1/3 of its original size. If the server is removed because the data has decreased, it will lead to a reduction in computing power and a decrease in the number of CPUs allotted to other tenants. Similarly, although the data volume on DB2 tenant has not changed, the SQL load has increased and causing an increase in QPS and requiring more CPU computing power. In this situation, we must increase the number of servers. This will fix the data volume issue, but will add unneeded compute capacity to the environment, making it more expensive and potentially harder to manage. Finally, we have the DB3 tenant. The amount of data is doubled, and it is obvious that it requires double the number of servers. Once again, we have the problem of excess compute capacity. I think it's safe to say that unified storage and compute leads to situations where you have unused resources because if you need compute, you must add storage, and if you need storage, you must add compute. This architecture is inflexible, it's difficult to control, and it's costly. We've seen the problems with scaling environments where compute and storage are coupled. Now let's take a look at TiDB and see how separating compute from storage makes our lives easier. So TiDB separates compute from storage. Compute is handled by TiDB server. Recall that this is the component that applications connect to. It handles SQL processing. Storage is handled by TiKV, and TiKV is a key value store. If we are constrained on the compute side, we add TiDB servers. If we are constrained on the storage side, we add TiKV nodes. The opposite is true too. If we have excess compute capacity, we can remove TiDB server nodes. If we have excess storage capacity, we can remove TiKV nodes. Once again, let's talk about the load variability among our three tenants that we discussed previously. So recall our previous discussion about DB1. Its data volume is decreased to 1/3 its original size. I know what you're thinking. Applications never decrease their storage volumes. Bear with me here. The SQL workload remains unchanged. So using TiDB, we only need to remove TiKV nodes that originally stored TiDB tenant data, TiDB1 tenant data. and TiDB server ensures that SQL processing capability remains constant. Oh, the user experience remains the same as well. DB2 has consistent data volume. On the other hand, it needs additional compute power. We address this by adding TiDB server nodes to the environment. Adding more CPU and RAM to DB2 ensures acceptable query response times. DB3 needs more storage. We can increase the number of TiKV nodes to address this. There's no need to increase the number of TiDB server nodes for DB3 because, well, we don't need to do that. As you can see, splitting compute and storage makes our lives much easier. It also reduces cost because we don't have to pay for resources that are not needed. As I mentioned previously, Forrester Research made up the term translytical to describe a new generation of data platforms that combined transactional and analytical processing capabilities within a single environment. So let's discuss multi-tenant clusters that do not possess translytical capability. That is, do not possess this ability. So traditional single and multi-tenant databases often cannot handle transactional and analytical business simultaneously. They require time-consuming ETL conversions to be implemented in two different database systems. For example, you run your transactional workload in Oracle and your analytic workload in Teradata. This approach requires multiple systems and an ETL process to move data from the transactional system into the analytics system. This is a lot of work and usually winds up being a maintenance nightmare. On the left-hand side of the diagram, we see our old friends DB1, DB2, and DB3. Although I haven't mentioned it, these databases are primarily transactional in nature. In other words, are focused on OLTP. So let's assume that the single-tenant architecture DB1 has a requirement for online analytics processing, or OLAP. We would need to set up a new system for OLAP, that is, install a new environment, and we would need to develop an ETL process to move data from the OLTP side to the OLAP side. Let's look at the right-hand side of the diagram. If we move to a multi-tenant database that doesn't include translytical capabilities, we must set up a similar environment. The main problem with this approach is that we don't have one environment that can handle both OLTP and OLAP. In the world of analytics, data stores, and databases, columnar storage is popular. Columnar databases can aggregate data rapidly because they don't have to read through all the data in a row. There are multi-tenant databases that include both row-based and column-based data on a single server. This gives the first impression that multi-tenant databases simultaneously support row-based data replicas for OLTP business and column-based data replicas for OLAP or OLAP business. The key issue is that this design does not separate OLTP workloads from OLAP workloads. OLAP workloads typically consist of SQL operations that consume a lot of I/O and long-term CPU power, such as generating reports, evaluations, or risk analysis. Storing row-based and column-based data on the same server results in unpredictable response times for our OLTP workloads. The reason for the unpredictability is the long-term CPU usage of OLAP workloads. This means that OLTP queries may not meet their response time requirements. Let's summarize by saying, storing row-based data and columnar data on the same server is not a good solution for tenants who have both OLTP and OLAP businesses. TiDB solves many of the OLTP and OLAP problems we discussed on the previous slide. TiDB is designed to store row-based data and columnar data in a single environment. As we mentioned previously, row-based data is stored in TiKV. TiDB also provides a storage engine for columnar data. This storage engine is called TiFlash. You may be asking, why does TiDB provide different engines for two storage types? Well, we do this to ensure that the columnar storage operations do not adversely affect row storage, and so that row storage does not adversely affect columnar storage. This empowers TiDB to service both online transaction processing and online analytics processing. Each and every TiDB tenant can use TiFlash storage. In addition to storing data in columnar format, TiFlash uses a massively parallel processing computation architecture that is extremely efficient for large table joins and mass data aggregation. It's important to note TiDB requires available TiKV storage. On the other hand, TiFlash storage is optional. You can choose to use it based on your use case. For example, Table 2 has both OLTP and OLAP use cases, so we use both TiKV and TiFlash engines. Fortunately, TiDB handles all the data replication between the TiKV and the TiFlash sides, so there's no ETL or ELT required. It just works. Table 1 only services an OLTP use case, therefore we only have to have TiKV storage allocated to it. Remember, each table must have TiKV storage allocated to it. When you separate compute and storage, users benefit. Users don't need to know about TiKV and TiFlash because the TiDB optimizer, which lives in the compute layer, chooses which one to use based on the SQL. Speaking of SQL, and this is really cool, assume that you have a table named foo, which only has TiKV, that is row-based storage. The DBAs decide to add TiFlash columnar support to the table foo. Your queries will be able to use both engines without you doing anything. The compute layer, TiDB server, automatically routes operations that require precise indexing to the row-based TiKV and routes operations that require full table scans and basically large scans of data to TiFlash. This was previously unimaginable for a single tenant system relying on ETL tools. These single tenant users had to know which database to use for their SQL statements. We have a great name for this, and it's called HTAP, HTAP, and that means Hybrid Transactional and Analytic Processing. So in summary, TiDB's HTAP design for multi-tenancy allows us to have both row and column store versions of data with resource isolation. We no longer need to worry about synchronizing data between disparate row and column stores. We don't even need to consider which database to execute SQL queries on because TiDB is a single environment with a single SQL interface. We get to determine on a table-by-table basis whether or not to add column or data to a table. All of this is based on our use cases. In order to create and manage our TiDB multi-tenant database, we need tools and utilities. When you're getting started, the most pressing need is database operation. This includes installs, Kubernetes management, and backup and recovery. Fortunately, we have this covered. TiUp is a tool that helps users install, manage, and upgrade TiDB components. TiUp simplifies the installation process by providing a single command line interface to manage all components of the TiDB system. It also helps with version management, so users can easily upgrade or roll back to previous versions if necessary. TiDB Operator is a tool that helps manage and automate the deployment of TiDB clusters on Kubernetes. TiDB Operator combines the benefits of both technologies by enabling users to deploy, manage, and scale TiDB clusters on Kubernetes with ease. It automates the process of creating, updating, and deleting TiDB clusters and also monitors the health of the cluster components. TiDB BR is a backup and recovery tool that helps to create, manage, and restore backups of TiDB databases, ensuring that users have a reliable and secure way to protect and recover their valuable data. Next, we need to monitor our environment to ensure that it is working properly. First, we have Prometheus and Grafana. They're two popular open source tools that are widely used in the monitoring and observability of software applications and systems. They provide a powerful and flexible way to monitor and visualize the performance of TiDB clusters. They allow users to quickly identify and troubleshoot issues and make data-driven decisions about their TiDB clusters. TiDB Dashboard is a web-based user interface for managing and monitoring TiDB clusters. Although similar to Prometheus and Grafana, TiDB Dashboard is a centralized management and monitoring tool for TiDB clusters, while Prometheus and Grafana are monitoring and visualization tools for more focused on collecting, storing, and visualizing metrics data. Although there's some overlap in their functionality, they serve different purposes in the TiDB ecosystem. Next up, we have Clinic. Clinic is a performance analysis and optimization tool that helps users to identify and optimize the performance of their TiDB clusters, providing a valuable tool set for managing and optimizing large or complex TiDB deployments. Finally, we have the data platform. TiDB Dumpling is a tool that helps export data from TiDB databases. It allows users to export data into various formats such as SQL files or CSV files, making it easy to backup or transfer data into other databases. TiDB Lightning, on the other hand, is a tool that helps import data into TiDB databases. It is designed to be fast and efficient and can handle large amounts of data. TiDB Lightning uses the TiKV import mechanism, which allows it to quickly load data into the TiDB cluster. That means that basically you're bypassing SQL processing when you load this data. TiCDC is a utility that captures and replicates changes in TiDB databases in real time, providing users with a powerful tool set for managing data replication in the TiDB ecosystem. TiDB Data Migration is a tool in the TiDB ecosystem that helps migrate data from third-party databases to TiDB databases. And finally, Sync Diff Inspector is a utility that helps identify differences in data between two TiDB clusters. Let's return to the purpose of database consolidation. It helps to reduce cost and improve efficiency. Previously, we discussed that the cost problems in multi-tenant databases are often caused by the different needs of each tenant. Some tenants need more storage, some tenants need more computing power. This causes problems such as increased cost for storage and compute. It's also wasteful because if a system needs more storage, you have to add compute too. This is where TiDB and its separation of compute and storage save the day. If you need compute, add compute. If you need storage, add storage. The TiDB database provides some fine-grained control functions for resources, such as resource control that can allocate computing power and storage capacity on demand without unnecessary allocation. Placement rules and SQL control differentiated high availability levels. Classifying data storage as hot or cold helps us save money as well, and differentiated scale based on storage and computing power that can expand or shrink each tenant individually. All these help us refine cost control, and only by doing so can we adjust cost allocation based on differences of each tenant. TiDB Database's resource control can automatically schedule more computing power or storage capacity for tenants whose load suddenly increases or decreases. Features such as hot and cold separation and HTAP are effective functions aimed at ensuring that the system response and user experience are not affected after integrating data from multi-tenant databases. Therefore, we can see that choosing a suitable multi-tenant database for database consolidation can be crucial in reducing cost and increasing efficiency through fine-tuned control, and this is something that we must consider. So to review what we discussed, resource control helps with cost and efficiency. Placement rules in SQL also help with cost and efficiency. Scale helps with cost, and HTAP with efficiency.
If you want to learn more, scan this barcode and then you can get access to more PinCap training and certification resources.